Hey guys, NAT QoS here. In today's video, I'm going to talk about NAT. I'm going to cover three different types of NAT. Static NAT, dynamic NAT, and PAT, or Port Address Translation. I'm then going to jump into QoS, or Quality of Service, and I'm going to take a step back and discuss why we need QoS and the different techniques we can employ to use QoS, and also as an engineer or as a sales engineer, what are some of the key questions we have to ask in order to be able to come up with a QoS policy. So this is going to be a very realistic, real world, exciting video. Get pumped and let's roll. Welcome to CCNA 200-301 course. Today, I'm going to cover Section 4, Part 2. This is a continuation of the previous IP services section. Today, I'm going to wrap it up with NAT and QoS. Here are the topics I plan on covering today. I'm going to first do a deep dive into NAT. I'll do a NAT overview, talk through a few NAT concepts, then I'm going to talk about the different types of NAT, and finally, I'll wrap it up with configuration. I will then get into the QoS section. I'll provide an overview of QoS, classification and marking, queuing, shaping and policing, and finally, congestion avoidance. Let's go. Let's first talk about NAT. NAT stands for Network Address Translation. NAT is about mapping private IPs to public IPs. And the private IP address range is defined in RFC 1918, and here are the three ranges. So the first range defined in RFC 1918 is 10.0.0.0 all the way through 10.255.255.255. It could also be abbreviated as 10.0.0.0/8. The next range is 172.16.0.0/12. And the final range is 192.168.0.0/16. If you were to look at this diagram here, guys, you got the PCs at the bottom that are connected to a switch. And we have a LAN IP range 10.1.1.0/24. And on the external side of our NAT router, the range is 98.228.196.0/29. Now, what ends up happening when we enable NAT is that the NAT router takes our private IP address and maps it to the public IP. So what that means is, you see in IPv4 header, this 32-bit source address is swapped. So what NAT router does is it takes this source address that initially came from, so let's say if one of these guys down here below, let's say if Bob is using a machine that ends an IP address of 10.1.1.100, this guy right here. If this guy wants to ping some machine on the internet, that traffic is going to go through the switch up to the NAT router. NAT router will then perform a translation. It will swap out the source address of the LAN with the source address of the WAN, and it will do that mapping for us, and eventually the traffic shows up on the internet. And when the internet device sees that traffic, it actually sees the IP address of the external side of our router. It never sees that the traffic actually came from the inside of the router. It assumes that the traffic came from the outside of the router, and it's able to respond back. And you may be asking yourself a question at this point: why is that the case? Why do we need NAT? Can't we just route traffic everywhere on the internet? And you would be correct. Yes, you can, but here's the challenge. Remember, ISPs, or Internet Service Providers, deny private IP address space of RFC 1918 on their Internet Edge routers or Internet PE routers. PE stands for Provider Edge. They drop that traffic. ISPs by default have access control lists or ACLs in place to drop traffic that originates from the RFC 1918 private IP addressing space, because that traffic doesn't belong on the internet. That's the whole point of this RFC 1918. And that's exactly what allows different companies around the world to use the same IP addressing. So case in point, in your home office, you may have your machines be configured with the IP address range of 192.168.1.0/24. And at work, you may actually have the exact same space. And yet, at home, you can access the internet, and also at work, you can access the internet. Well, how could you do that? If there were potentially millions of people using the same addressing space, which is actually the case, then how could they access the internet? There would be a conflict. Well, what ends up happening is NAT, or network address translation, is what takes the private IPs, maps it to the public IP or IPs. It just depends on the configuration, and we'll talk through those details in a bit. And that traffic eventually makes it to the internet. That's the whole idea of NAT. Now let's dig slightly deeper. So if we were to take this NAT router and draw an imaginary line that delineates between the LAN private IP address represented in green going south and the WAN or the public side going north, the whole idea is to logically delineate between the private and the public side of our router. And what NAT does in this case is it takes the source IP of, let's say, if the machine at the bottom, .100, access a website located on that web server 80.1.1.1. When it opens up a browser and wants to access that web server, if you were to zoom into the layer 3 packet, we'll see what we're seeing on our screen here to the left. Source IP is 10.1.1.100 and the destination IP is 80.1.1.1. When this traffic makes it to the router, the NAT router then will swap out that LAN IP with the WAN IP. It's going to change it to 98.228.168.3 before the packet is sent to the web server. When the web server gets that traffic, it's never going to see that it came from 10.1.1.100. What it's going to see is that the traffic came from 98.228.196.3. It will respond back to that IP, and eventually the NAT router will then do what's called a translation between the public and the private IPs, and eventually that traffic will find its way back to Bob's PC of .100. Now, to continue building on that, another concept that you want to think about is the LAN side from a NAT perspective is also called the inside of our network. And the outside interface of our router facing the internet is considered outside. There's a terminology in NAT that I want you to familiarize yourself with to really understand how NAT works. The first term is inside local address. Now, as the name suggests, it's inside of our network and it's local to us, meaning 10.1.1.0/24 range cannot be routed on the internet. Because like I alluded to earlier, RFC 1918 IP address space is blocked by all the ISPs around the globe. Nobody allows it. So that traffic will die at the edge of our internet boundary. So that's defined by local inside address. The other term that's very critical for you to know is inside global address. And sometimes people get a little confused with this term, but I want you to pay close attention to it. The IP address of 98.228.196.1 on the outside of our router is actually considered an inside global address. And the reason it's considered inside global address is because it's inside of our network, but it's globally routable. But it's inside, meaning it's in our jurisdiction. It's in our administration. It's in our control. That's where the term inside comes in. Now, when the router creates a NAT translation table, it actually maps the inside local address to the inside global address. Like literally, it uses that terminology when we're doing show commands, and I'll show you that momentarily. But that's exactly how the router is able to keep track of all the traffic that's going through it. So this web server that we're trying to access on the internet, 80.1.1.1, is considered an outside global address. Why is it outside global address? Well, it's outside of our network, outside of our control, outside of our administration. We're not controlling it. Whoever has that web server is in charge of that IP, right? It's their domain name and IP mapped to that domain name. And it's global because it's routable on the internet. And the final term that I want you to pay attention to is outside local address. Now, this is a unique bird. In 99% of the situations, you're never going to come across this. So in reality, you shouldn't actually even worry about it. But for completion's sake, so think of it as the name suggests, it's outside local address. So local address means it's not routable on the internet, but it's outside of our control. It's outside of our administration. So think of it as if you acquired another company and now you want to connect your network with that company's network and they have their own local IP that you want to route to. In real world, you're going to come across it maybe less than 1% of the time. So I would suggest don't even worry about it. The terms you really want to understand are inside local, inside global, and outside global addresses. There are 3 different types of NAT. The first type that I want to talk about right now is static NAT. It's a one-to-one mapping between local and global IPs. So for example, your ISP might assign you a public block of 98.228.196.0/29, and then you may have your own LAN private IP block of 10.1.1.0/24. And what you might do is you might go ahead and map these manually. It's a very manually driven configuration. And the way the NAT router translation table, after you have done configuring things, the way it's going to look like is you're going to have, for example, 10.1.1.100 machine mapped to 98.228.196.3. You may have the other machine, the one that ends in .101, mapped to a different IP, 196.4. And then the third machine, the one that ends in 102, might be mapped to 196.5. So you have 3 different entries that actually manually define how your NAT is going to be configured. Now, before I move on to the other types, I think what would make it a lot easier if I went ahead and showed you this on a command line. So let me go ahead and jump on command line. So here I am on the command line interface. I've got the diagram for you below so it's easier for you to manage. Instead of 3 machines that I was showing in the previous slide, I only have 2 machines. To the left, I have Bob and Leah connected to a switch. Then that switch connects into the CE NAT router. CE here stands for Customer Edge NAT because it's at the edge of our network. And then we have an internet circuit that's coming in from our ISP. And our ISP gave us a block of /29. And you're connected to their internet provider edge router. And then I have a loopback created on the provider edge to represent this web server of 80.1.1.1. Okay, it's not an actual web server as you're seeing in the diagram. I'm just trying to simulate a web server through a loopback interface just to keep things simple and easier. Now that said, I'm currently on the CE NAT router, and let me go ahead and configure static NAT because that's what we just finished talking about. So the first thing I'm going to do here is I'm going to go ahead and go to my global configuration mode, and I need to go ahead and define my inside interface and outside interface. So step 1 is define my outside interface. So I'll do IP NAT outside. Okay. So this says that my fast Ethernet 00, which is pointing to my provider edge internet circuit, that's the outside of my NAT. And I'm then going to exit, and I'm going to type in interface fast 1/0 and type in IP NAT inside. That suggests that our fast Ethernet 1/0 represents the LAN side of our network. Once I'm done, the final step in static NAT is that I'm going to manually define my NAT entries. So in global configuration mode, I'm going to type in IP NAT inside source static, and then I'm going to go ahead and type in my inside local address first. So 10.1.1. Bob's PC first, which is 100. And then I'm going to define my inside global address, which is 98.228.196.3. The reason I'm using .3 is because, as you can see in the diagram here, we can't use 0 because that's the network address. .1 is assigned to the provider edge. .2 is assigned to our router's interface. So .3 is the first available IP in this range. And the other NAT entry that I'm going to create here is for Leah's PC. So I'm going to type in 10.1.1.101, and I'm going to give it the inside global address of 98.228.196.4, and I am done. So now I'm going to go to Bob's PC and I'm going to ping 80.1.1.1, and I'm successful. I'm now going to go to Leah's PC and type in ping 80.1.1.1. So as you can see in this diagram, guys, I went to Bob and Leah's PC and I was able to successfully ping the web server located out on the internet through my infrastructure in between. So what that tells me is that NAT is doing its job because I'm able to successfully hit the IP address of 80.1.1.1. So to demonstrate that NAT is working correctly in our machine, I'm going to type in show IP NAT translations. And this is showing me that I actually pinged, which is the ICMP message. I pinged this machine right here, 80.1.1.1, successfully from my machine, which is the outside global address. And then it also shows that Leah's PC, which is right here, 10.1.1.101, was also able to ping 80.1.1.1 on the internet. So that's pretty cool. Now another command that I want you to keep in mind is show IP NAT statistics. What this command shows us is that we actually have two active translations in our NAT translation table right now, and they're both static type of NAT entries because we manually created them. So that's static NAT for you. The next type of NAT I want to talk about is dynamic NAT. Now, it's very similar to the static NAT, with the biggest difference being that it's dynamic one-on-one mapping. Before, we manually did the mapping. This time, it's more of a dynamic mapping between local and global IPs, and I'll show you exactly what I mean when we're on a CLI in a moment. Now, the ISP assigned block is the same as before. Our LAN block is still the same. And the big difference here is instead of doing one-to-one mapping, it's a lot easier if you could just map a pool of LAN IPs to a pool of WAN IPs. When we have a couple of entries, that's easy. But if you have hundreds and hundreds of machines that need to be mapped, it's a waste of time to do one-to-one mapping. It's a lot easier to just dynamically define that. Now, how the router maintains its translation table is going to look exactly the same as static NAT. The only difference is this time it's dynamic. Now let's quickly jump on CLI so you can actually see the difference between static and dynamic. So here I am back on the customer edge NAT router again. I'm going to go to global configuration mode, and I'm going to go ahead and start configuring dynamic NAT this time around. Now, this is a 5-step process. The first step is that I'm going to define my inside and outside interfaces. So I'll do interface fast 1/0, and I'm going to say IP NAT inside. I'm then going to go to interface fast 00 and say IP NAT outside. So these steps are identical to what we did previously with the static NAT. Now, here's where the difference starts. We're going to first define our access list. Let's just say access list 10. We're going to permit our LAN range, which is 10.1.1.0, and with the wildcard mask of 0.0.0.255. And by the way, in this case, what this access list is doing is, instead of permitting, even though we're using the keyword permit, here we're actually matching. So when the traffic comes into our NAT router that matches this access list, we're going to do something with that traffic. So that's what's happening here. Now, I know we haven't talked about access lists yet. That's the next section that I'm going to do when we move to the next section, section 5 of this exam. But until then, just hang in there with me. Just consider this a super high level overview of access list. And the next thing we're going to do here is I'm going to define my IP NAT pool. So I'm going to say IP space NAT space pool. I'm going to call it DN for dynamic NAT. And then I'm going to define my starting IP. So I'll say 98.228.169.3. Once again, the NAT pool that I'm defining is the NAT pool of the inside global addresses, right? And then I'm going to define the final IP in this range, which is 98.228.196.6. And I'm going to provide the net mask value of 255.255.255.248. And that is how you define your NAT pool. And the final thing that you want to do that kind of brings it all together is the access list that we created and this pool that we just created. We now have to connect these two things together. And the way we do that is we type in IP NAT inside source, and we're going to call on the access list that we created. And then we're going to call on the pool that we created called dynamic NAT. And that pretty much creates the configuration piece for us. And I'm now going to go to Bob and I'm going to go ahead and ping that IP again. And sure enough, I'm still able to access the web server on the internet of 80.1.1.1. Going back to the NAT router, I'm going to type in show IP NAT translations, and it shows me that my machine, or I should say Bob's machine of 10.1.1.100 is able to successfully ping the IP of 80.1.1.1. And same thing with Leah. Leah was able to also successfully ping, and we can also see that because it says ICMP protocol. That's what this flag is. Pro means protocol. And that wraps up dynamic NAT. All right, before I explain the last type of NAT, I want to show you a quick command that is very helpful. So if you want to clear your NAT translations, here's the command that will wipe off all the NAT translations in your current NAT table. It's clear IP NAT translation star. Right after that command, when you type in show IP NAT translations, all the translations are gone. Now let's go back to the slides and wrap up NAT. This is the final type of NAT that CCNA talks about. By the way, there are some additional NAT types, but they're beyond the scope of CCNA. We'll probably cover some additional level of depth in CCNP, but even beyond that, there's carrier grade NAT. And so I encourage you to do some Google search if you're interested in learning beyond what's covered in CCNA. But at this point, I know for some of you, it's like drinking from a fire hose. I will wrap things up with this third and final type of NAT. It's called PAT. And PAT stands for Port Address Translation. What happens with PAT is we take a bunch of LAN IPs and we map that to a single public IP. And where it comes in handy is because, as you guys know, we're out of IPv4 addresses. We actually ran out of IPv4 addresses a few years ago. And port address translation is what has allowed the life of IPv4 to be extended, because we don't need, for every single LAN IP, we don't need a one-to-one mapping with a public WAN IP. We can have hundreds or even thousands of LAN IPs that are mapped to a single WAN IP address that's publicly routable on the internet. And PAT is also called NAT Overload. And the NAT translation table looks different on the router when it comes to PAT. And what ends up happening here is that, as you can see, the 10.1.1.100 address has colon and a port number in front of it. This is called an ephemeral port or private port. And the reason it's called ephemeral is because it's short-lived. After it has served its purpose, it just goes away. And it's a range of port addresses that you can use. For more details, watch my previous video I did on transport layer. And the first address that we show in this table gets mapped to the inside global address of 98.228.196.2 colon 50,101. Now, what ends up happening is the router automatically generates these port numbers, and they're different from the port numbers that are generated by the machines or the operating system. If you're using a Mac or Windows, they generate their own dynamic ports or private ports. But in this instance, the router also generates its own set of dynamic ports, so it can keep track of the communication that happens. And then so on and so forth, as you see on the screen. But the common denominator here, as you can clearly see in the inside global address section of the table, is that it's the same address, the one that ends in .2, but it has different port numbers attached to it. Hence the name port address translation, aka NAT Overload. Now let's quickly jump on the CLI and take a look. Now let's configure PAT on our router as shown below, CENAT. I'm going to go to global configuration mode, and the first step is, it's a 4-step process. The first step is we define our inside interface. So I'll do interface fast 1/0 and I'll say IPNAT inside. I'll then go to my external interface and say IPNAT outside. So we're done with 2 steps. The third step here is I'm going to go ahead and create an access list. I'm going to call it access list 10. I'm going to say permit 10.1.1.0. We have done this before. And the final step, we need to go ahead and map this access list to the action that we want it to take. So now we're going to say IPNAT inside source. We're going to call on the access list here, which is 10, and we're going to say interface fast 00, which happens to be our outside interface, and you're going to add the keyword overload and hit enter, and that's it. So now what I'm going to do is I'm going to go to Bob and I'm going to try pinging 80.1.1.1. Sure enough, I can ping it. I'm now going to go to Leah and try to ping. Sure enough, I'm successful. Now let's go back to the CENAT router and let's go ahead and look at show IP NAT translations. And here's our translation. Now, the common denominator here, as you'll see, is our inside global address remains the same. But as you can see, it came from 2 different hosts. It came from Bob sitting on .100 and Leah sitting on 101. Clearly shown under inside local address, and the outside global address, of course, is the address of the web server here, and it's ICMP traffic, which is ping. And that wraps up the NAT section. Now let's shift our attention to QoS. Before I get into the mechanics of QoS, let's ask ourselves the question, why? Whenever you learn a new piece of technology, it's crucial to take a step back and ask yourself, why does this technology exist? What problems is this technology designed to solve? If you make this a habit, I promise you, your level of understanding will be completely transformed. With that, let's jump into why QoS. First, QoS stands for quality of service. Here I've got a very small network, and what I have in that network is 2 servers, each connecting at a 10 gig level. So I've got potentially 20 gig worth of capacity being utilized from downlink's perspective. But if you look at the uplink on the switch is limited to 10 gig. So that's a 2-to-1 speed mismatch. And then when we go from the switch to the router, the WAN circuit that we have is 1 gig. So that's actually a 10x mismatch. So as you can see, as we continue going upstream in our network, we have more choke points. And the speed mismatch causes packets to sit in the buffer, which is a place in memory. And traffic just sits there until it's processed. And what causes traffic to sit in the buffer? If way more traffic is coming into the device, then its ability to be able to deliver traffic on its outbound interface, then that traffic has to be queued somewhere. It has to sit in a buffer somewhere. And that's where QoS comes in. As I just finished talking about, these are the 2 network choke points, the uplink from the switch into the CE or the customer edge router, and the WAN circuit that is terminating on our CE. Now, here are today's network challenges. So if you think about your voice flow, for example, if you happen to be on a Zoom call or Skype or Microsoft Teams or WebEx, your voice packets are very small. Contrast that to somebody who's on YouTube watching a 4K video or ultra high definition video. It's going to absolutely crush your voice flow. And that's not a good thing. That's a terrible thing. There is a way to manage that, but it is a challenge that we have to look into. Also, your business mission critical traffic must be prioritized over less critical traffic. So if you happen to be a retail shop, definitely the credit card swipe is the most critical traffic to your business. That has to be prioritized over guest Wi-Fi, for example. Also, the real-time traffic, such as voice and video, is time and delay sensitive. I'll talk more about the real-time traffic in a bit. And finally, in today's network, the expectation is that there's going to be 0 downtime. Network that's always available all the time, like any other utility, like water or power. Now that said, let me give you a quick overview of QoS. So hopefully up until this point, I've built a business case for you to understand that we need traffic management technique. And that's exactly what QoS is. Because when we have a traffic mismatch or choke points in our network, that traffic has to be dealt with. And that's where QoS comes in. It helps us manage peak bursts in our network. Now, one key thing I want you guys to keep in mind is if your network is congested all the time, QoS is not going to solve your issue. You absolutely need to upgrade your bandwidth. QoS will only come to rescue if your network is congested at certain times of the day. For example, first thing in the morning when people walk into the office to log in, you're going to see a little peak there. Also, certain times of the day when there are certain activities that get kicked off, like some sort of backup, that can be managed with QoS. But if your network is congested all the time, you have bigger issues. You absolutely need to upgrade your bandwidth. The whole idea of QoS is to provide unfair advantage, as I like to call it, to certain types of traffic on our network. And naturally, you might be asking yourself a question, why would we want to provide unfair advantage to certain traffic? Well, let me give you an analogy. So if you have a 10-wheeler truck, like the one you're looking at, and then you have a beautiful Lamborghini right behind that 10-wheeler, well, the Lamborghini could go 200 miles an hour, whereas that truck might only go up to 80 miles an hour. Well, we got an issue. Plus, the truck is much bigger, and let's imagine if it's a single lane road, Lamborghini is going to be stuck behind that truck for a while until we get out of the one lane situation. So in our network, what we do is we create unfair advantage for certain types of traffic, which in this case is a Lamborghini, to allow it to have priority so it can actually get past the truck because it can move faster. Other examples could be like ambulances and fire trucks having the ability to use emergency lanes to be able to provide services to the community. So we're, in a sense, providing an unfair advantage to them so they can provide better service to the community. Similarly, in QoS, we have the ability to allow certain type of traffic to be able to provide better customer experience to our users. And there are 4 key attributes of network traffic that we must absolutely know about, and we have to know them cold to understand and master QoS. First is bandwidth. Second is delay. Third is jitter. And fourth is packet loss. Now let me dig deep into each. So what's the bandwidth? Now bandwidth is the speed or capacity of the interface in bits per second. So for example, Bob's laptop might be connected into this customer edge router at 1 gig, and the other interface on the CE might be plugged into the web server at 100 meg. Now as you can see, there is a 10-to-1 mismatch when it comes to bandwidth or speed. So what this would do is the laptop will have the ability to send a lot more traffic into the CE than the CE is capable of forwarding over to the web server. Now this web server might have different types of traffic. It may have, of course, the web traffic, and it may also serve some other, if it's a unified server, it might have the ability to process voice and video. So to deal with this traffic mismatch and to do this efficiently, what the router would do is it would create different queues. Okay, so it will create, let's say, QA, it will create QB, so on and so forth. And it might say that, hey, all the voice traffic can be put into QA, and all the data traffic could be put into QB. And the voice traffic will get a high priority over the data traffic because the data traffic can be dropped. If you guys remember UDP and TCP, voice and video use UDP, whereas data uses TCP. So TCP traffic can be retransmitted at layer 4 or transport layer, whereas voice traffic gets dropped. If it gets dropped, it gets dropped. It doesn't get retransmitted. So we have to give it a high priority. So if there's a mismatch like this, voice will always be processed and sent to the web server, whereas data traffic can be selectively dropped. So this is a very high-level rudimentary example, but I'll dig a lot deeper as we continue moving forward. The next thing I want to talk about is delay. Delay is the time it takes for a packet to travel from source to destination. So Bob could be the source and web server could be the destination. It's the amount of time it takes for the packet to travel, and that's what we call a one-way delay, because that's how long it takes for a packet to go from Bob's laptop to the web server. But if you were to measure traffic in both directions, for that flow to go from Bob to the web server and then come back around, that entire thing is called round trip delay. Because what we're capturing now is the amount of time it takes for the packet to go back and forth. The third element here is jitter. Now, jitter is a variation in one-way delay between continuous packets or a packet flow. So for example, Bob may send multiple packets. So let's say the first packet sent experiences a latency of 100 milliseconds. The second packet may experience a latency of 120 milliseconds. And then the third packet sent may experience a latency of 150 milliseconds. So as you can see, between the first and second packet, we have a discrepancy of 20 milliseconds or delay of 20 milliseconds. And between the second and the third packet, we have a delay of 30 milliseconds. This difference in delay is called jitter, and it's an absolutely terrible thing, especially for voice and video real-time traffic. And finally, packet loss. Now, packet loss is the amount of lost packets on an interface represented as percent of lost packets. So in this example, if Bob sends 10 packets and the web server only gets 5, that means we had a 50% packet loss, and that is terrible. In times of congestion, traffic gets dropped, and QoS tools can help us manage that aspect. Now let's talk through different types of traffic. I've got this chart here to show you how different types of traffic on our network is treated and whether or not it's delay and jitter and packet loss sensitive, because that is the most crucial thing to know before we learn the mechanics of QoS. What I have on the left is network traffic types. So the first type of traffic that I have here is network control traffic, which is reserved. The second type of traffic is voice and video, that's real-time traffic. The third type is mission critical, and the fourth type is bulk data, things like email, file transfer. Now the network control traffic is reserved. That is not something we can change or manipulate. Routers and switches automatically prioritize their network control traffic on anything else. When I say network control traffic, what does that mean? Things like spanning tree at layer 2 or OSPF or BGP at layer 3 or routing protocols. That traffic must be prioritized because that's what allows switches and routers to build paths and traffic flows. So that path has to be available for the network to continue operating. So that is always super prioritized. And network control traffic is delay sensitive, jitter sensitive, packet loss sensitive, because it absolutely has to function before anything else functions. Now, voice and video traffic is also delay sensitive, jitter sensitive, and packet loss sensitive. The mission critical traffic typically is delay sensitive, may not be jitter sensitive, and it may not be packet loss sensitive, especially if it's TCP based. It can always be retransmitted, so it's not really sensitive to packet loss. And bulk traffic, because that's primarily all TCP traffic, it's not delay, jitter, or packet loss sensitive at all, and it's considered the lowest priority traffic on our network. Now let me quickly cover best practice service levels when it comes to voice and video. So for voice over IP, what's the best SLA or service level agreement according to Cisco? Cisco says as long as the delay, one-way delay, is 150 milliseconds or less, if the jitter is 30 milliseconds or less, and if the packet loss is 1% or less, then that's considered a good quality voice service level agreement, or SLA. Now, why do we call it an SLA? This is sort of an agreement with the business that the network is going to provide a certain level of quality to certain types of traffic so the business can continue operating smoothly. Because you can imagine if the voice quality is bad and you have a customer on the other side who's very upset, and every other word that they're saying you cannot hear because of a bad network quality, they'll get even more upset. And that's terrible. That's where the SLA comes in. Now, next up is video SLA. And according to Cisco, if the bandwidth is between 384 kilobits per second to 20 plus megabits per second, it depends whether we're dealing with a 720p or 1080p or a 4K ultra high definition traffic. Also, the delay one way between 200 to 400 milliseconds, jitter between 30 to 50 milliseconds, and packet loss of 0.1% to 1%. That's considered a good quality video SLA for any business out there. Now, as you can clearly see, video traffic is more sensitive to packet loss than even voice traffic. So something to keep in mind, whereas video traffic is less jitter sensitive and less delay sensitive, clearly. Now let's take a step back and walk you through what it takes to implement quality of service in real world. So this is based on my experience as an engineer in the industry. When I'm talking to my customers, this is my approach of collecting all the data points to be able to figure out how we're going to deploy quality of service. So the first thing you would want to do is gather customer requirements and identify types of traffic that they have in their network. The next thing you do after you have identified the traffic is divide that traffic into different type of classes, specifying if it's voice, mission critical, best effort, so on and so forth. And finally, in step 3, you define your QoS policy for each class. So you may say voice gets the highest priority, mission critical gets the next level priority after voice, and best effort you could care less because it's mostly TCP based, web surfing and all that. If it gets dropped, that's okay. It can always be retransmitted. Now, let me zoom into each step to give you a more deeper understanding of what I mean. So step 1 is customer requirements and traffic types. So here, the first step is we gather business requirements. So we identify business critical applications. So we ask the business, we audit the business, right? We go and talk to different business stakeholders and we go, hey, what are the key business applications you run in your network? So the customer might say, I have email, I have SAP or Oracle, and I've got these different storage systems and all that. And that helps you then create your quality of service policy. And the next thing you do is you also gather network requirements. So you identify various types of traffic on the network, traffic like voice over IP, traffic like video, traffic like database, and video surveillance, for example. And then after you have all those data points that you have gathered from your business and network audit and interviews, you then use that information to define service levels for these different applications and traffic types. And that leads to step number 2, which is you divide that traffic into different classes. So the email traffic will get the best effort type of mapping. The application traffic may get the transactional level, which is a guaranteed delivery. The e-commerce and web browsing, because that might be critical to your business, will get guaranteed delivery as well. And you'll classify it as mission critical traffic, whereas voice would be considered low latency, super mission critical, and you'll put that in the low latency, whereas best effort doesn't get any delivery guarantee. And then you have scavenger class, which is less than best effort. Maybe for your business, this could be social media type traffic or certain websites like Netflix and others that are super bandwidth hungry and they might bring your network to a crawl. What you do is you just proactively give those classes super low priority so they don't crush your network during times of congestion. And the final step is step 3, you define QoS policy for each class. So as you can see on the right hand side, when you're all done with step 1 and 2, you may say, hey, ABC Corporation gets this network QoS policy. Voice traffic is an absolute priority. ERP system is critical priority. Manufacturing system is critical priority, whereas web surfing is not allowed during business hours. And you create a QoS policy. And what that means is you define different service levels of QoS for each class of traffic. And one thing I want you guys to keep in mind is QoS is a per hop behavior, or PHB. What does that mean? Everything that we have talked about so far, each device in our network, each router, each switch must have quality of service configured on it for this policy to operate correctly. So let's say if you have a server that gets plugged into a switch, and then that switch plugs into another switch, and then that switch plugs into a router, and eventually it connects to the internet, that entire chain must have QoS configured. Every single hop along the way must have QoS configured. Otherwise, it's not going to work. Okay, that's the only way it's going to work is when everybody understands how the traffic must be treated when it arrives and that traffic sits into the queue at each hop. Now let's shift our attention to QoS tools and techniques. So the first one is classification and marking. That's the act of categorizing traffic into different classes and then you put labels on each packet as it comes into the network. So case in point, I have this router at the bottom of the screen, and we got these packets coming in. And what we'll do then is we'll categorize those packets or put labels on those packets. So as you can see, I've got blue, orange, yellow, green. And then once we do that, the next step is we'll define queues, because that traffic, if the incoming traffic is more than our outgoing capacity or the bandwidth, then the traffic is going to have to sit in a queue. By default, routers and switches implement what's called FIFO queue, which stands for first in, first out queue. That's not really quality of service. That is just first come, first serve basis, if you will. Now, it's a good strategy when you go to a restaurant, or you want to go watch a movie, or when you go visit a particular store during Thanksgiving. All good, but FIFO is absolutely terrible way of dealing with traffic. So what we do is we use QoS, which allows us to create multiple queues for providing priority treatment. So on our router, we'll literally create different queues, as I'm showing on the screen here. And then once those queues are created, we then look into shaping and policing. Now, shaping and policing is a strategy within QoS that allows us to throttle or rate limit traffic. So what does that mean? Let me show you through this animation. So we have these packets that are coming in, right? We labeled them or we colored them, then we put them in queues, and then they zoom through the queues. And then we decide based on our strategy what we're going to do with each queue. So in this scenario, for example, the top queue, the blue one, as you can see, I'm allowing all the packets to go through. So this might be voice, and the one below it might be our mission critical traffic, the orange one. And the one below that might be the best effort traffic, the yellow one. And then the green one might be the scavenger traffic, which is absolutely terrible traffic in our network. We don't want it, and will severely limit it in ratio compared to the other packets that need priority on our network. And finally, we can employ a technique called congestion avoidance, and it's used to deal with packet loss. And the whole idea is we proactively discard some packets to begin with before filling our queue. That ends up leading to congestion. So just kill those packets and don't even allow them to get into the queue. Now, let me go deeper into classification and marking. Now, classification, as I alluded to previously, is the process of looking at packets and then putting those packets in different classes based upon a certain predefined criteria, like access control lists. Predefined criteria could be the incoming interface, IP precedence, DSCP, source or destination address, or application. Now, I will go deep into IP precedence and DSCP momentarily, so don't worry about those terms for the moment. Without classification, all you get is FIFO, which isn't really QoS, and I explained that on the previous slide. Cisco suggests classifying traffic as close to the source as possible. So what that means is, if you think about the access layer, right? So you have a server or a PC plugged into a switch. Now that's the very first point in the network where the device is connecting into our network. According to Cisco, we would want to classify our traffic right then and there at the access layer level. This way, we're able to deal with that traffic in a very nice way across all the hops. If we don't do QoS at the very first hop that traffic jumps on our network, then it may not get the type of treatment we want that traffic to get. So that's the logic behind classifying traffic as close to the source as possible. And then the next element that is very important is marking that traffic. And what that means is putting a label on each packet or coloring each packet. So here's an analogy. If you think FedEx, they have different types of shipment: ground shipment, 2-day shipment, overnight shipment. Now, let's say if you paid a lot of money for an overnight shipment and your envelope didn't get to its destination the next day, you'll get very upset because you paid a lot of extra money for the overnight shipment compared to ground or the 2-day shipment. Similarly, in the network, we have a very similar type of strategy that we can employ using QoS by labeling traffic with different types of priority and how we want that traffic to be treated throughout our network. Finally, labeled packets can be subjected to different QoS treatment. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're gonna have to be a little patient because I'm working on designing an entire CCNA course. I'm gonna do an official launch in the next couple of months, but until then, I'm gonna keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.